This lesson is on multiplying and dividing radical expressions. In order to do this, we first want to perform any operations, whether it's distribution or just a multiplication or squaring something. Once you perform the operations, you want to simplify any radicals. Remember, radicals are roots, and you want to simplify radicals as explained in the previous videos. Then you can collect any like terms, and if you do have radicals in your denominator, you're going to need to rationalize them. So at the end of this video, we go over rationalizing denominators. Let's look at a few examples of multiplying radical expressions. Here we have just plain multiplication operations, so we're just multiplying. Now remember that a root multiplied by a root, if it's the same degree of root, so they're both square roots, can be seen as just a root of the insides. So we looked at this property in a previous video where the root can split over multiplication. So once we've multiplied, here we get 6 times 8, which is 48. So this is the same as taking the root of 48. Now, the next step we wanted to look at, after performing the operations, was to simplify any radicals. So we have a radical here and we want to simplify it. Notice, to simplify it, we want to look at what 48 is made up of so that we can find any perfect squares to reduce. Well, 48 came from 6 times 8, so you almost don't even have to multiply these. You can just keep breaking them down further. So it was 6 times 8, 6 was 2 times 3, 8 was 2 times 4, 4 was 2 times 2. So you could right away go from 6 times 8 to breaking it down to 2 times 3 times 2 times 2 times 2. I'm going to rearrange it so all my 2's are together and all my 3's are together. That way, I can now see that I have one pair of 2's, another pair of 2's, and a 3 that's left alone. So each pair of 2's, remember, is like taking the root of 4, which becomes 2. So that really we just have 2 times 2 outside of the root, which is 4, root 3. If you're lost with this, you should go back to the previous video on simplifying radical expressions. Now let's look at one where we have numbers outside and we have radicals as well. Remember that if you have something written as 2 root 10, that's the same as 2 times root 10. And this is the same as negative 3 times root 5. Because multiplication is commutative, you could see this as 2 times negative 3 times root 10 times root 5. You can rearrange them in any order. So, in this case, we're seeing that the roots are multiplying and the numbers are multiplying. This is all multiplication. This bracket doesn't really need to be there except for keeping the negative in. So what's happening is you have 2 times negative 3, which is negative 6, and you have root 50. And now we need to simplify root 50. So 50 is 2 times 25. 25 is a perfect square of 5 times 5. So we can write it out. We get 2 times 5 times 5. The double 5 becomes a single 5 because root of 25 is 5. And we get negative 6 times 5 root 2, which is negative 30 root 2. Now that is completely simplified there. In this next example, we now have cube roots. So we can also merge the roots if we're multiplying cube roots because they're both cube roots. So underneath, we've got cube root of 12 times 6. But now, remember that a cube root causes us to look for triplets of common factors. So let's break this down into factors. So 12 is 3 times 4, which is 2 times 2. 6 is 2 times 3. So we actually have a nice triplet of 2's. 3 2's become 1 2 in taking a cube root of that, because that's the same as cube root of 8 becoming 2. Now these two 3's, they don't form a triplet, so they have to stay. So 1 2 comes out, and we have a cube root of 9 left inside. Let's try the last one here. So remember, the numbers stay as numbers and they can just multiply because this is all multiplication. You can multiply in any order. So you've got 6, and then we've got root, and then we were doing x times x cubed. X times x cubed is x to the 4. Now remember, you can take half of the exponent because we're grouping these x's into groups of 2. So we've got 6. And if you wrote it out, you'd have 4 x's. So you can imagine that you'd have 2 groups of x coming out, leaving you with x squared. Next, we have multiplying radical expressions. However, here we're going to be using distribution properties. So we're not only going to multiply 2 items, we're going to have to distribute and make 2 multiplications. So here we're multiplying root a by root 5a and then root a by 3. So let's start with root a times root 5a. This first example I'm going to write out quite completely here, but you don't need to write it out this much every single time. But let's just look at what's happening. We're doing root a times root 5a. So just like on the previous slide, this would be one question. And then we're adding, because plus times plus is positive, root a times 3. Now we want to combine any roots within the multiplication. So we've got root of 5a squared. It's all multiplication in there. Plus next term, and usually we write the numbers before the root so that there's no confusion as to where the root ends. So we got 3 root a. Great. Now, because we've performed the operations, we want to simplify the roots. So the only thing that we can do here is take the a square and make it an a, and you're left with a root 5 plus 3 root a. So we've simplified the roots, and now we're looking for like terms. Do we have any like terms? Now that's the point of simplifying the roots, is so that when you do expand it, it's easier to see if you have any like terms or not. In this case we don't. The root 5 and the root a are not the same. So that's all we can do with it. We don't have any denominators here, so there's nothing to rationalize. Let's try the next one. So if you remember, when you have a bracket squared, that's the same as going bracket times itself. So don't fall into the trap of squaring each of those components. So now we're going to use distribution, and now I'm going to talk through it and kind of skip that step of writing things out. So we're going to right away put them into the multiplied format. So let's talk it out. X times x gives us x squared. X times negative 2 root 3 will give us negative 2x root 3. The order that is most desired is number in front, any letters in alphabetical order, and then any roots, also with the same order. Okay, next one will be negative 2 root 3 times x. So that's also a negative 2x root 3. It's all multiplied in here. And the last one will be positive 4 root, and this root will be a root 3 times a root 3, which is a root 9, which becomes just a 3. Notice we're actually kind of like squaring that last term, right? So if you're squaring 2 root 3, it's going to become 4 times. Squaring a root is 3, so that's 4 times 3. Either way, you get x squared minus 2x root 3 minus 2x root 3. Hey, those sound like terms, but let's look at that in a sec. Plus 4 times, and root 9 is 3, so that's just 4 times 3. So that 4 times 3 is going to become a 12. Now we can collect any like terms. We have like terms of x root 3, so we have negative 2 of those, minus 2 of those gives us negative 4 of those. X squared minus 4x root 3 plus 12 is the simplest form you can take it to. Let's try this last question here. We've got cube roots, and remember cube roots mesh with cube roots, so that's great. Cube root of a times cube root of 2a squared is going to give us a cube root of everything multiplied inside, so 2a cubed. Cube root of a times 2 is just going to be plus 2 cube root of a. Now let's simplify. The only thing we can simplify here is the a cubed. A cubed means you have 3 a's, and that's a triplet. So that becomes an a out of the root. You still have a cube root of 2 left. In the next one, we cannot simplify it, so that's all we can do. The terms are not like terms because they have different endings. So you just leave it if nothing else happens there. Now let's take a look at some dividing radical expression questions. Remember, when you're dividing radical expressions, if you have a fraction, you never want to leave a root in the denominator. That's just mathematical practice, not to leave the root in the denominator. Also, you may have seen some of these before when learning how to simplify roots. And in the past, whenever we have some sort of fraction and you have an exponent on it or a root on it, you're trying to simplify the inside first. Remember, the root can split over division, so this is essentially the same as taking root 18x cubed over 75x. Simplifying the inside is a good practice because it just makes things quicker most of the time. So 18 over 75 simplifies to be 6 over 25. And x cubed over x simplifies to be x squared on top. Once we have it simplified, we can consider taking the root and considering simplifying the top root and the bottom root. Now, the top root, 6 is just a 2 times a 3, and those don't simplify at all. There's no pair there, so that's going to stay. But x squared can be rooted, and 1x will come out of that. So you'll have x root 6 over root 25 is 5. Because that's 5 times 5, it's a pair of 5s, 1 5 comes out. Now, our root is simplified, and there's no root in the denominator. There's no common factors, so we're done. Let's try the next one. So let's simplify the inside first. I mean, you don't have to simplify the inside first, but it's good practice. Makes the process a bit quicker here. So if you simplify 16 over 54, you end up with 8 over 27. And x to the 9 over x to the 6 will leave you with x cubed on top. So now we're considering cube rooting 8x cubed and cube rooting 27. If you cube root 8, you'll see that's 2 times 2 times 2. So that's a triplet of 2's, and x cubed is also a triplet of x's. So you have a 2 coming out and an x coming out, leaving you with 2x, and there's nothing left in the cube root. Awesome. In the denominator, we have cube root of 27, and 27 is 3 times 3 times 3, which is a triplet of 3's, which is just 3. You could also notice that when you type in cube root of 27 on your calculator, you just get a 3. So, no common factors here, no roots in the bottom, and we have no root at all, so we don't even need to make sure that it's simplified. So that's done. Now, remember, we can't have any radicals in the denominator. So here are some examples where we actually need to rationalize the denominator. Let's look at the first one. So all of these examples here I've chosen because they have one radical term in the denominator. The next slide, you'll look at 2 radical terms. So if you have one radical term, take a moment and think about what you could multiply this root 3 by so that there's no root left anymore. Okay, if you've thought about it, you should be thinking that, yeah, root 3. If you multiply root 3 by root 3, what do you get? You get root 9, which is 3. Now, if we do multiplication by root 3 in the denominator, then we need to do that in the numerator as well. So, you're basically multiplying by something that will eliminate the root. So, this leaves us with root 3 over, and this was a times, so that's 2 times root 9, which is root 3 over 2 times 3. We wanted to multiply by root 3 because that caused it to become a perfect square, which then simplified to a nice integer. That leaves us with root 3 over 6. And this is the desired way of writing 1 over 2 root 3 because there is no radical in the denominator. One reason for doing this is later if you're trying to add fractions with radicals in the denominators, it's easier to find a common factor or a common denominator if you just have integers in the denominator. Let's look at the next one. Think about what you would multiply cube root of 2 by to eliminate the root. Okay, so now it's not that easy because if you multiply by cube root of 2, you'll just have cube root of 4, which is cube root of 2 times 2. Does that help us? No. But what if we made it a triplet? Hey, that would work, wouldn't it? That would be cube root of 8, which is just a 2, a nice integer. So what's missing? You only have 1, 2 given under the cube root. So if we multiply by cube root of 2 times 2, which is cube root of 4, that will cause it to triple up and then simplify. So sometimes you just have to be a little clever here to come up with what you would multiply by in order to lead to the next perfect square or perfect cube, depending on the root that you have given. Okay, so we're multiplying numerator and denominator by cube root of 4. That leaves us with 5 cube root of 4 in the numerator, and this led to this. Cube root of 2 times cube root of 4 was cube root of 8, which is 2. And that's done because cube root of 4 cannot simplify further. 5 and 2, no common factors, no root in the denominator. Great, that's what we need. Next one here. What would you multiply root 12b by in order to eliminate the root? Well, you would need to multiply by root 12b, because if you only multiply by root 12, you'll cancel the 12, but the b will still be left in a root, and you don't want any roots left in the bottom. So let's multiply by root 12b. That's going to give us now 3 times root 12ab. Notice all the stuff in the root multiplies together. And in the denominator we get, what do you think this will make? Well, this will make root 144b squared, which simplifies to 12b. Notice it's just one version of the under the root part. Okay, now, is everything simplified here? Well, no, actually we have a common factor between the 3 and the 12. We can divide them both by 3, getting 1 over 4. And in the root here, we have a root of 12. So remember, root 12 is root 3 times 2 times 2. We have a pair of 2's. So we want to make sure the roots are simplified as well. The root actually becomes 2 root 3. The a and b stay inside. So we've got, basically, this became root 3 times 2 times 2 times a times b. And this was a 4b in the denominator. And the 2 came out, and the rest was left inside, giving us 3ab over 4b. 2 root 3ab over 4b is now simplified and rationalized. Now, continuing on our no radicals in the denominator examples, here are some examples where there are 2 radical terms in the denominator. So, this may take a little bit more thought to get rid of the root. Let's play around a little bit here. We have 1 over 1 plus root 2. What if we multiplied by, and think of something and try it, and check it out, see if it works. A lot of people will say multiply by root 2. So let's do that. Multiply by root 2. And what do we get? You get root 2, but then what's in the denominator? Oh, well, that's going to distribute and leave us with root 2 plus root 2 times root 2, which is 2, because that cancels. So yeah, we got rid of one root, but then another one appeared. Yikes. What else could we multiply by? Multiplying by just one single term didn't work because it simplified one of them, but not both of them. So we need some heavier artillery here to get this whole bracket to somehow multiply by something so that there are no roots left. How do we get rid of roots? Well, we want to make sure they're squared. Can you think of something where we multiply 2 brackets together and all of the terms resulting were squared? That would be useful. If we could have both of these terms somehow be squared, then we would have eliminated our roots. So, recall this formula. A squared minus b squared was the expansion of an a plus b times an a minus b term. These 2 brackets here, the positive version and the negative version, are called conjugates. So, what you're doing here when you're simplifying, you're trying to multiply the denominator by its conjugate to eliminate any radicals. So, what is the conjugate of 1 plus root 2? Well, the conjugate just means the opposite sign. So 1 minus root 2 would satisfy that. Because we multiplied the denominator, we also want to multiply the numerator. Great. Let's continue and see how this works. So the numerator, we've got 1 times 1 minus root 2, so the 1 distributes in and is leaving us with 1 minus root 2. In the denominator, now we can use our difference of squares formula, which tells us square the first minus square the last. Sure, you could go ahead and multiply everything out, but at this point in the course, you should be familiar with this formula. So let's take it using the formula. We take our first term squared minus our last term squared, which leaves us with 1 minus 2. And in the numerator, we have 1 minus root 2. So that gives us 1 minus root 2 over, and 1 minus 2 is negative 1. So if we're dividing both top numbers by negative 1, we actually get a change of signs going on. So it's like 1 divided by negative 1 is negative 1, and negative 2, root 2 divided by negative 1 is positive root 2. So that's a much simpler version of 1 over 1 plus root 2. Actually, this can also be written as root 2 minus 1. It really doesn't matter how you arrange it as long as it's simplified. So yeah, root 2 minus 1. Nicer way of writing 1 over 1 plus root 2. Let's try the next one. Here, we also have two terms in the denominator. So, notice that I'm putting brackets on both numerator and denominator, and I'm going to multiply by something that will eliminate roots in the denominator. I don't really care if there's roots in the numerator. So here, a common error would be to choose the conjugate of the numerator, but then you're going to cancel them in the numerator but not the denominator. So what is the conjugate here? Well, the other version of 2 minus root 3 would be 2 plus root 3. And we therefore have to do that in the numerator as well. So let's run that through its course. In the numerator, we need to expand. So first times first gives us 2 times 2, which is 4. Then we have 2 times root 3, which is positive 2 root 3. Then we have 2 times root 3 again, positive 2 root 3. And then we have root 3 times root 3, which is root 9. And root 9 is just a 3, so let's just write it as a 3. In the denominator, we have our difference of squares formula, which is first term squared minus last term squared. The numerator actually was a formula too, but you could use the formula or expand. So in the denominator, we have 2 squared minus root 3 squared. Nice. We're going to eliminate the root because we're squaring it. So that leaves us with 4 plus 3, which is 7. And these are like terms, 2 root 3 plus 2 root 3, so that's plus 4 root 3, over. And then we have 4 minus 3 in the denominator, which is just a 1. So because the denominator becomes a 1, 7 divided by 1 is 7, plus 4 root 3 divided by 1 is 4 root 3, and we're done. Let's take a look at the last example here. We've got root x over root x minus root y. To rationalize the denominator, we want to eliminate any roots in the denominator. So we want to multiply by the conjugate, root x plus root y, root x plus root y. And that leaves us with, in the numerator we have root x times root x is root x squared. Root x times root y is plus root xy over, and this is a difference of squares, so we can just treat it as a squared minus b squared. That's root x squared minus root y squared, which will just become x minus y because squaring roots eliminates them. And here we get x plus root xy. So that's about as simple as we can go. You could separate it as x over x minus y plus root xy over x minus y, but this is just fine as long as it's simplified. So there you have it. You have eliminated any roots from the denominator, and any roots in the numerator are simplified, and there are no common factors to further cancel.